Hello and welcome to Daily Dose of DevOps. Today we're going to talk about containers and two key components of containers that the Linux kernel provide. This is a very common interview question. I feel I've gotten it multiple times. I've also given it. If you have anything on your resume related to containers or Docker or Kubernetes, you may get this question or questions kind of similar to this. Before we get into the key components of containers, let's define what a container is. And this can have varying definitions. The definition I like to use is that containers are a standalone executable unit that encapsulate all necessary dependencies, libraries, and configuration files required for an application to run consistently across various environments. And before I get into a demonstration of these key components on a shell, let's talk about a basic concept: containers versus traditional virtual machines. So let's use an analogy here. Think of traditional virtual machines like houses, okay? Each house has its own complete infrastructure: plumbing, electricity, walls, and a roof. Similarly, each VM has its own operating system and all necessary components to run applications. This isolation is great, but it comes with a lot of overhead. In contrast, containers are more like apartments in a high-rise building. They share the same foundational infrastructure, the building itself, but have their own isolated living spaces, the containers. This shared foundation reduces overhead and allows for more efficient resource usage. Let's get to the key components of containers. First one are namespaces, which is an isolation mechanism, and the second are control groups, C groups, or resource management. There are more components of containers, but these are the two main that we're going to talk about today. The first one, namespaces. Imagine namespaces as curtains inside and around your apartment. These curtains provide privacy and isolation from other apartments in the building. In the context of Linux containers, namespaces isolate the container's processes, the network, the mounts, and more from the host and other containers. Some important types of namespaces, and there's more than just these three, but we'll talk about just these three for now, are the PID namespace, and this isolates process IDs, so a container can have processes with the same IDs as those on the host or other containers without conflict. There's also network namespaces, and each container can have its own network interfaces and routing tables, just like having a separate interconnection in each apartment. And another one is the mount namespace. This ensures that file systems and directories appear differently inside the container than on the host. The second key component are control groups, or C groups. Think of C groups as the building's utility management system. It controls how much electricity, or CPU, water, or memory, and other resources each apartment or container can use. C groups limit and monitor the resource usage of containers to ensure fair distribution and prevent any single container from hogging all resources. So let's demonstrate namespaces first. So in the Linux terminal, we're going to use the unshare command, and this will run a program with some namespaces unshared from a parent. So if we run unshare fork exactly like this, mount proc bash, this command creates a new process, a new PID namespace, and mounts a new proc file system instance at /proc. So we'll use psaux, and we'll see that in this new namespace, there's only one bash process running with PID1. The namespace is init process. So we can exit out of this namespace. We can also demonstrate namespaces by, let's run a Docker container. It's going to pull the Alpine image, and we are inside the container. So you can see if we run a PS in this container, we just see the sh command, which is how we ran the container. If we run a df here, this is going to show file systems that are just particular to this container. So this is how namespaces work. This is how the isolation works. We can also run an IPADDR to see that this container actually has its own IP address as well. Let's exit out of this container, and let's launch another container to demonstrate namespaces. So here we launched a container called MyEngineX3. Let's grab the PID for this container, 4586, and let's inspect the namespaces. So once we have the PID, we can list the namespaces using the ls command. And you can see here, this will list the namespaces that the process and the container it's running in is associated with. Each link in this directory is a symbolic link to a namespace. So you'll see here the PID, you'll see net, you'll see MNT, you'll see UTS. So this also demonstrates to you namespaces. Now, if we also wanted to demonstrate here Cgroups, we can also run an ls and, we can also cat the proc PID cgroup, and we can actually here see each corresponding line is actually a cgroup that this process is a part of. So as you can see, Docker creates a new cgroup for each launch container under each cgroup subsystem, memory, CPU set. So if you wanted to examine the actual settings and limits imposed by cgroups, you can also look into the actual cgroups file system. And this cgroups file system is usually mounted under sys fs cgroup. For example, to see memory-related settings for this container, you would look under, let's see, memory, Docker, and we can see, let's run an ls for this container. Here you will find numerous files whose names and contents tell you about limits and usage stats related to memory management for this specific container. So that's one way to explore cgroups more. So today we went over the definition of containers, and we went over the key components that the Linux kernel enables: namespaces, which is an isolation mechanism, and control groups, which is a resource management mechanism. So thanks for listening. Subscribe to my channel. Thank you very much.